Section 11.3 is going to continue our discussion about angles. We're going to talk about relationships specifically between angles here at the beginning. One relationship that angles have is they could be vertical angles. So vertical angles are pairs of angles that appear across from each other whenever two lines intersect. So I'll mark two vertical angles on our picture. So this angle in pink would be considered vertical angles. They're across from each other. There's another pair of vertical angles here as well. Do you guys see it? Yeah, the top and the bottom. So whenever we have intersecting lines, they form two pairs of vertical angles. And vertical angles are congruent. Now that doesn't mean that the pink and the orange are congruent here. It means the pink and the pink correspond to one another, are congruent. The orange and the orange correspond to one another. They are vertical angles and are congruent. Another relationship that will exist depending on how things are corresponding is complementary or supplementary angles. So complementary angles are two angles whose measures add up to 90. We say that these angles complement one another. So the diagram on the right-hand side there has lots and lots of angles. So we wouldn't talk about all those angles being complementary because it's always the description of two angles that add up to 90. But I'll draw a picture within that. If I talked about angle, wow, that was not straight at all. Let's try again. If I talked about this orange angle right here, where it extended this piece, it would have a complementary angle to this red angle right here, covering those three smaller angles, because the red and the orange angles considered add up to 90. Now that's not the only pair of angles that I could have done, right? I could have chosen something different. I could have chosen this one, for instance, and this one. The same thing would happen. So any two of them that add up to 90 are considered complementary angles. The other one here on this slide is supplementary angles. So supplementary angles are two angles that add up to 180. We say that these angles supplement one another. So in our diagram here, there are a couple of pairs of supplementary angles. So one of them would be right here in the yellow, along with the orange. Those would be supplementary angles. They add up to 180. Or we could have chosen to do this angle and this angle, and they would add up to 180 as well. All right, one more on this front page that is a relationship one. Other types of angles can be formed when we have a transversal in play. So if we have two lines that are parallel, you can see here L and M are parallel, and we have another line that crosses through both of them, and actually L and M don't have to be parallel for the definition to work. They just often are, so let me back out of that. L and M, and then they are crossed by a third line T here. The angles that you see formed here actually create different kinds of relationships. Now, some of those relationships are ones we've already discussed. I bet you can pick out a couple of vertical angles, right? Probably a bunch of them. I bet you could pick out some supplementary angles in this imagery, right? Bunches of them. So a lot of the angles we've talked about can be created by the same diagram. Specifically with this diagram, we can also talk about some other descriptions of the angles. Interior angles. Interior angles are angles that would lie between the pair of lines, and the lines that it's referencing are lines L and M. So when it's talking about between the pair of lines, that's what it is referencing. Whoops, wrong color. So between L and M. So if you take a look at this picture, what angles do you see that are between lines L and M? 2 and 7, and what else? And 3 and 8. So these are our four, what we would call interior angles. So the interior angles here are angle 2, angle sorry, 7 was what you told me. 7, angle 3, and angle 8. Those are my interior angles. And as you switched to the other page, we have a more descriptive phrase calling it alternate interior angles. So alternate interior angles are angles that are interior, first of all, and they have to be on opposite sides of the transversal. So in my image here, there are 2 pair of alternate interior angles. So one of them would be 8 and 2. Those would be alternate interior. So angle 8 and angle 2. Another pair of alternate interior angles would be to put 7 and 3. Angle 7 and angle 3. Now we'll get to the why on that, we'll get to another fact about that in a moment that you may remember. Generally speaking, we can't really say a whole lot about those 2 angles. However, specifically if L and M are parallel, then we can say that those alternate interior angles are congruent. So if they're parallel. We have the same kind of descriptive showing up for the exterior angles. Exterior angles are angles that are outside of the 2 lines. So in my picture, what are my 4 exterior angles? 1, 4, 5, and 6, right? They are outside of the pair of lines, not between them. And then if they're outside, they're exterior angles, and they're on opposite sides of the transversal, then they are alternate exterior angles. So 4 and 6 would be 1 pair. And then the other pair present in this diagram would be 5 and 1. And again, there's nothing that we can say in general about them, but if we know that they're parallel, they will create them to be equal. They'll be equal valued. So that's what's going on this. Oh wait, one more. Corresponding angles. I was jumping ahead to the next slide. Corresponding angles is the last one. Corresponding angles are angles that are in the same position where the transversal intersects one line and where it intersects another. For example, this angle 4 is sort of on the top left-hand corner of this intersection, right? Well, that's the same position that angle 7 is of this intersection. So we would say that angles 4 and 7 are corresponding angles. And we can do that with all the pairs in all the locations. So how about the top right, angle 1? Well, it'll correspond to angle 2. So angle 1 and angle 2 have that same corresponding relationship, corresponding angles relationship. We can do 8 and 5. Or we can do, I got 3 and 6. So there are 4 pair of corresponding angles. So again, there's a congruency that happens with these corresponding angles, but only when the lines are parallel. So that's what this last piece is talking about, corresponding angles. What if the corresponding angles are congruent? Well, the reality is that all 4 of these bullet points are all interchangeable. If you know one, you know all 4. If the corresponding angles are congruent, then alternate interior angles, alternate exterior angles are congruent, and lines are parallel. If lines are parallel, then all 3 of these things are congruent, right? This is one of those things where if you get one, you get all 4. If one fails, they all 4 fail. These are all synonymous descriptions of what happens. One naturally hangs on the other. All right, so I want to talk about constructing parallel lines using a triangle. There's a very interesting way that you can create parallel lines, and that actually is talked about on page 659 of your book. So I'm going to go through it with you. I know you've got page 659. You can read it on your own later if you want some more details. But we're going to construct it by starting out with this. We're going to let M be a line. And P is a point not on M. Okay, so we're going to draw our line. You can draw it in this space that you have there, either on the left side or the right side or whatever. Just draw yourself a line. You can draw it vertically, you can draw it horizontally. I think since I've got some grid marks, I'm just going to draw it horizontally right there. So there's my line. It could be at a slant. And I need, so that's line P, I'm sorry, line M. And here's my point P not on M. I may end up shifting P closer if I find out I'm off the screen by what I keep drawing. I'm not sure. We'll see. All right, we're going to create triangle ABC. Where one side of the triangle lies on M. Okay, so I'm going to draw my triangle just so that it's not running into anything. I'm going to draw it down here. And we'll call this, for lack of any other good reason, the ABC in this order. There's nothing special about that. I just need to designate it, so that's what I'm designating it to be. All right, the next thing we're going to do is we're going to lie a ruler alongside, I didn't say that right, alongside, as in two words, alongside AC. Okay, so if you can imagine, I don't know if I have a ruler up here or not. Yeah, I do. All right. So if you can imagine taking your ruler and you're actually just lining up the ruler down here. Everybody good? All right, cool. And what we're going to do is we're going to take that triangle. Like if you were really doing this, you'd actually cut out a triangle, and that's what you would do. And you could actually cut the triangle out to the same size. And we're going to slide. I've got to move P down because now it's running into all my words, and I'll move my words up so I have more space. Slide the triangle ABC along the ruler until line AB, the part that's currently along side M, or line M, so line AB, or side AB, intersects P. This will form line L parallel to M because the corresponding angles are congruent. I'll abbreviate. Okay, so if you can imagine, I'll change my color so that it's easier to see it move. And it isn't going to be perfect, but just pretend for the moment. So here's the triangle it's referencing for triangle ABC. And over here in red, we'll go with, is going to be my ruler that's going to be the slide red. And we're going to slide the yellow triangle up the side of the ruler. So if you can imagine, we are going to end up eventually with my triangle being up here. like so. This is not perfectly drawn, but you're going to imagine the triangle is now up here, shifted, right? And it's going to have created this other line up here at the top, right here, the line that contains that point P. But what I know, because I simply moved the triangle itself, is that I know, for instance, that this angle and this angle are the same, because they were from the same triangle, just shifted. And if those corresponding angles are equivalent, they're equal, they're congruent specifically, then according to this, it's one of those 4 equal statements, right? My lines would be parallel. It's clever, right? You could physically do this, right? You could actually create this triangle on a piece of paper. You could physically move it, not just virtually the way I'm doing it on this screen right here. And it would create that peachy colored line there at the top, line L, that would be parallel to line M. All right, I want you guys to do one more activity for me. We're going to actually do this one. So let me tell you what the status is for, or what we're trying to prove first. We're going to prove that the sum of the measures of the interior angles of a triangle is 180 degrees. And I can't remember if I have scissors in here or not, so let me pause just a second and see if I can find them. So you can make any style of triangle you'd like. I'm going to see if I can make one again. Oh, I'm doing a much better job of folding now. Thank you. I hope you are as well. My first fold was terrible. Okay, once you have folded and you've got your triangle, big enough that it's not, uber tiny. I think I spoke too soon on the tearing bit. Go ahead and label the 3 angles. Just A, B, C, 1, 2, 3, your initials, I don't care. Just 3 different letters inside. So at this point, you've got some kind of a triangle, whatever it is, and you're going to label A, B, C, or something else. Extra scraps can go in the trash. I don't need the scraps back. Thanks, Sylvia. Okay, who's still working on their triangle? Does everybody have triangles? Are we done with the triangle making at this point? Emily's still cutting on hers. Anybody else still cutting your triangle? Okay, a couple of you. Cut the triangle, label the letters. Depending on how neatly or how messy your tear might have been, it wouldn't be the worst thing in the world to try to kind of mark the edges that are supposed to be the straight edges on the sides on your triangle itself, because of what I'm going to ask you to do here in a moment. So if yours is really straight and you had a clean, nice cut because you had the scissors, you don't need to do that. But if yours is kind of shady, kind of mindless, like it's just like, whatever, you know, I'm gonna mark mine. Okay, the next thing you're gonna do is you're gonna take your triangle and you're gonna tear the 3 corners off. I know, you're like, wait, what? Now you really made a mess. All right, so you're tearing off your 3 corners. The tinier they are, the harder it is just to work with, but it doesn't really matter. So the next thing I want you to do after you've made your 3 tears is the corners that you marked, like I did on my screen, in red, or that you marked, however, whatever, that are the real sharp, you know, the sharp not the tears that you made that were like funny perforations just now, but the clean tears. You're going to use those to line them up. So these are going to line up, and you're going to line all 3 of them up side by side. When was the last time you had a tape in a math class, right? Tape and tear construction paper, I mean, for real. Okay, I hope that your lining them up was cleaner than mine, because mine was kind of messy. What'd you notice? Wow. Those corners, when you put them together, form a straight line, at least they should, within some level of accuracy of our tearing, right? The 3 corners, when put edge to edge, those 3 vertices, end up creating a straight line. So it ends up looking something like this. Here was angle A. Doesn't matter what order you had it in, but then mine actually on my screen here has one angle B that's quite large. And then I have angle C right here, and all the way around from left to right is a straight angle, and we already established previously that straight angles are 180 degrees by definition, right? That is one proof by tearing a piece of paper. We're going to call it that. Proof by tearing a piece of paper that the angles in a triangle add up to 180 degrees. Okay, so that's fun, right? If you want to tape your thing into your paper, I mean, depending on what size it is, if you want to tape it into your notes, you could do that. There's lots of tape around, so just grab one of those sheets. If you want to throw it away and you just want to draw it in there, that's fine too. I'd like to talk with you through a few more shapes before we pause for today. So that's a triangle. We could actually do the same argument if we wanted to for a quadrilateral. We could create a quadrilateral. I could do a parallelogram, and you could do a rhombus, and you could do a rectangle, and somebody else could do a trapezoid, and somebody could do something that's none of it are, you know, all the angles are different or whatever. And we could tear the 4 corners apart. We could line them all up. They wouldn't create a line though. They would create a complete figure all the way around. Not necessarily a circle because we've, you know, torn all the pieces, but the angles in the middle would create a full 360 degree angle. So if we have a quadrilateral, they're actually 360 degrees. Now the picture over here that I want you to see, another justification aside from my proof by tearing a piece of paper for a triangle, is that you can see that if I take the quadrilateral, I could cut it into 2 triangles, right? And if I know that each triangle has 180 degrees, I think that's a little too thick. What do you get when you add 180 and 180 together? You get 360. So another justification, aside from proof by tearing a piece of paper, is we could split our image into triangles. Now, once we get bigger than a quadrilateral, there's no proof by tearing anything anymore anyway, because we've exceeded the 360 that we are able to visually measure. But if you take a look at the next picture, which happens to be a pentagon, how many triangles does it split into? It splits into 3. Now, it's important to realize that as you're splitting the triangle or splitting into the triangles, it has to split off of the same vertice, right? Like all of this is split from here. Okay? So in other words, I couldn't split it differently, and that'll come into play bigger in a more prevalent way in a moment. But I have 3 triangles, so there's 180 times 3. 180 times 3 is what? It is 540. Good. Then we have a hexagon. How many does the hexagon end up having? Triangles. How many triangles does it end up having? What is it?
4.
There are 4 triangles in the hexagon. What's 180 times 4? 720. So take a look back here. This one was 180 times 2. Then I had 180 times 3. Then I have 180 times 4. Right? So every side I add on another triangle. Agreed? In particular, it's 180. And how many triangles do I have? Well, when there were 6 sides, there are 4 triangles. When there were 5 sides, there were 3 triangles. When there were 4 sides, there are 2 triangles. I don't want you to count, but I want you to think with this pattern. If I have 12 sides, how many triangles am I going to have? More than 6. It'll be 10. Okay, those of you who got 10, why is it 10? It's 2 fewer, right? So when there's 4 sides, 4 minus 2 is 2. When there's 5 sides, 5 minus 2 is 3. When there's 6 sides, 6 minus 2 is 4. It's 2 fewer than the number of sides. That's how many triangles you have. So whatever your number of, so I didn't put this in the right spot. I'm sorry. This 180 was supposed to go down here. My bad. So sorry. Erase that. Your number of triangles, that's what I was trying to fill in, is 2 less than your number of sides. It's 2 less than the sides. So our formula or our description is that we would take n minus 2, which is the number of triangles, 2 less than the number of sides, and multiply it by 180 in order to find the degrees in our triangle. We will do one problem and then we'll pick up next time because it's a direct application. What if we have 37-sided polygon? You might want your calculator. So what would you do? 35, right? So 37 minus 2, which is 35. And what will I do with that 35? Yes, I will multiply it by a 180. What will that give you? 6,300 degrees. You do not want to draw a 37-sided shape, right? But if you did, that's what you'd end up with in terms of degrees. The other thing that you can be asked, and we will look more a little bit at this next time, is you could also be asked if this shape had all the angles equal, what does that mean an angle measure is actually worth in this 37-sided shape? We can take that 6,300 and we could divide by the number of angles 37 and we could find that value, and we will pick up there next time. So what we're going to do next is we're going to go back to doing the group work for 11.2, and 11.2 will be due on Friday.